Good morning, ladies. Today I'm going to do a heat and phase change problem for you. These are the problems when you're adding heat to something. You want to know how much heat is added to both change temperature as well as change phase of something. So today I have 1.2 kilograms of minus 2-degree ice, and I want to turn that into 40-degree water, and I want to know how much heat am I going to have to add to do that. So when you're approaching these problems, the first thing that I would do is write down exactly what happens step by step. You can do that either on a phase diagram that I've shown over here that always has heat increasing to the right on the x-axis and temperature increasing on the y-axis, or just writing it out in words. So I'll do both for you right now. What's the very first thing that's going to happen when you put that ice on the hot plate? It's minus 2 degrees. The first thing that's going to happen is that ice is going to heat up. It can't melt yet. It's not 0 degrees. Ice doesn't melt until it is 0 degrees. So that ice is going to heat or change temperature until when? Until it reaches 0 degrees. Because it can't go to 1 degree because then it's going to be water. So ice will change temperature until you have 1.2 kilograms of 0 degree ice. That's the very first thing that's going to happen. So now I have 1.2 kilograms of 0 degree ice, and I haven't turned that hot plate off. What's going to happen to that ice now? Now that ice can melt. After it melts, it's going to be a little bit of ice and a little bit of water, and they're both going to be 0 degrees until it all melts. All of that energy being added, all of that heat being added is being used to break those bonds of the ice and turn it into water. And I'm going to be left with 1.2 kilograms of 0 degree water. If I have 1.2 kilograms of 0 degree water, what the problem asks is how much heat do I need to add to make that 40-degree water. So I have one last step for this problem, and that's to say that 1.42 kilograms of 0 degree water, now that heat is going to be used to change that temperature to 40 degrees. On a phase diagram, it looks like this. We started at minus 2 degrees, and we started with the ice, and the ice heated up. It heated up until it reached 0 degrees. At 0 degrees, it began to melt, and during that time there is no change in temperature. After it melted and it was completely water, so I have here I have all ice. By the time I get here I have all water. 0 degrees, and now that's going to increase in temperature to 40 degrees. Obviously, that could increase in temperature if I continued to add heat up to 100 degrees, at which point you may have another phase change to steam, and then you can heat that steam up. But this problem only asked us to go through to the water. So this is step 1 in my words, this is step 2 in my words, and this is step 3 in my words. What do those steps look like in an equation form? Remember, for step 1, we're heating. When we're using heat to add, we use Q equals mc delta T, where C is the specific heat, and that's a constant for any given material. And in these phase change problems, we're always going to be using water. So for the first step, it's going to be an mc delta T, because we're changing temperature. The second step, we're melting. So in the second step, step 2, we want to use the heat of fusion. Q is equal to MHF. Again, these are all on your equation sheet. And for step 3, it's another change of temperature problem, so Q is equal to MC delta T. To find out how much heat we need from beginning to end of this process, we just need to add those 3 pieces together. So the full equation will look like Q equals mc delta T plus MHF plus mc delta T. We need to look at which C we're going to use and what our change in temperature is going to be for each of these steps. The mass is going to be 1.2 kilograms throughout. Remember, mass is conserved throughout this process. So the mass is going to be 1.2 kilograms. What is it we're heating in step 1? In step 1, we are heating up the ice. So we're going to use the C of ice that you can find right here. It's on your equation sheet, 2100 joules per kilogram Kelvin. And how much temperature change is the ice experiencing? The ice is experiencing 2 degrees of temperature change. Later on, we're going to heat the water some more. Be very careful. Many people like to write 42 degrees. They write the total temperature change. We are only heating the ice in step 1. In step 2, where we're melting, HF is a constant given on your equation sheet for water, and that's what we're going to be using here. And in step 3, we are going to be using the same mass, and now what is it we're heating? Now we are heating the water, so we're going to use the C of water, again, given right here. The change in temperature for step 3, you can see here on our phase diagram, or here in step 3, is 40 degrees. The water heats for 40 degrees, so we'll be using 40 degrees in here. Remember we talked about this temperature actually must be in Kelvin because our specific heat is measured in joules per kilogram Kelvin. However, we've shown that a change in temperature since addition's cumulative and we've added, or commutative, and we've added the 273 to each side, we don't need to go through that step. But please remember that the temperature that you're actually putting in here is in Kelvin, not in degrees, once you do your equation. Okay, so let's just plug some numbers in and see what we get. Our final answer is going to be Q is equal to 1.2 kilograms times the C of ice, 2100 joules per kilogram Kelvin. And that is a change in temperature of 2 Kelvin. Next is the melting phase, step 2, 1.2 kilograms times the heat of fusion for water, which is a constant, 3.34 times 10 to the 5th joules per kilogram. And the last step is another MC delta T, 1.2 times the C of water this time, times a temperature change of 40 degrees. Notice that our kilogram is in the numerator here and our kilogram is in the denominator here. And our Kelvin is the denominator here, Kelvin is in the numerator here. We're left with joules. Same thing over here. Our kilograms cancel and we're left with joules. This is also kilograms, joules per kilogram Kelvin, and again, our units cancel out to joules. That's great because we know that heat is measured in joules. It's a form of energy. And our final answer for this problem is 6.06 times 10 to the 5th joules.